Hello, in this short video we're going to look into truth tables. Truth tables are something used to describe the behavior of digital circuits. So whenever you have a digital circuit, one thing you're going to have common is it has some inputs and it also has certain number of outputs. Okay, and the truth table is nothing but the tabular representation of the relation between inputs and outputs. And the way we represent it is each column in the table represents an input or an output. And let's say we have a system with m number of inputs and n number of outputs. We would have a table with m plus n number of columns as stated in point 3. Now, that is the number of columns. But how does the number of rows is calculated? The number of rows is calculated by this formula here. If you have m inputs, the number of rows is 2 to the power of m. So let's look into an example here on the left side. We have a circuit with two inputs A and B, and we have one output C. So the number of input combinations is equals 2 to the power of m. M is the number of inputs, which is 2, so 2 to the power of 2 equals 4. So what we have here is a table, and as I said in point 2 here, each column represents an input and an output. So input A goes here, input B goes here, and output C goes here. So if you see, you have 1, 2, 3, 4. 1, 2, 3, 4 rows in this truth table. Now, how do we fill this truth table? The best way to start with is go with the rightmost input and look into here. If you have one bit, what are the different combinations? 0 and 1, right? Now, let's do the same thing. 0, 1, 0, 1, keep on writing that. Now, what we are saying here is for input A, B, we're trying to have 4 different combinations. We can have 4 different combinations. Here we are saying B is 0, so A could be 0 or 1, right? So the first two we fill 0, 0, the next two we fill 1, 1. That's it. Now let's look into an example we have on the right side here. We have a circuit with 3 inputs P, Q, R, one output T. The number of combinations are 2 to the power of 3, which is 8. So let's fill this truth table here. We have Q, input Q, input R, and output T. So how do we fill this combination? Just like the example on the left side, we go with rightmost, start with 0, 1, 0, 1, 0, 1, 0, 1. Now, move to the next left bit, and Q is do 2 zeros, 2 ones. Follow the same thing, 2 zeros, 2 ones, and go to the next one. So here, what we need, take a guess on what we are going to do here. Here we did 0, 1. We changed every other cell. Here we kept it same for every other cell. So here we're going to do 0, 0, 0, 0, 1, 1, 1, 1. That is how you fill a 3-input truth table. Now, let's look into a simple example problem, fairly quick. So we have a problem. Our inputs are x and y. Our output equals z. The problem is z equals 1 if both x and y are equal to 1. So let's see here. The number of rows in the truth table is 2 to the power of m. M is the number of inputs, which are 2 here. So our number of rows is going to be 2 to the power of 2, which is 4. So we have table x, y, and z. Rows are going to be 4 rows. So as we have seen in the previous example, 4 combinations are 0, 1, 0, 1. So we have 0, 0, 0, 0. Sorry, 1, 1. So output Z is going to be 1. Output Z is going to be 1 only if both X and Y are 1. So look into the cell where both X and Y are equal to 1. That is the only case here, is the last row here. So my Z is going to be 1 here. And if Z equals 1 here, only in this cell, what would be the remaining values? Since it is a binary, it could have only 0 or 1, and we gave a condition for Z equals to 1. So obviously, the only other possible value is that Z is going to be a 0. This is how you fill a simple truth table for a digital circuit.